In this lecture, we will learn how to estimate battery life of a device. So before we dive into the topic of battery life estimation, let us review some of the key terms and units that we are going to use. We start with voltage. Voltage is the measure of electric potential difference between 2 points in a circuit, and it is commonly expressed in the units of volts. It is the SI unit for electromotive force. Current is the measure of how much electric charge flows through a point in a circuit per unit time. And current is expressed in the unit of amperes, which is the SI unit for electric current. So to understand how much energy a device consumed, we need to know two important quantities: power and energy. So the power is the rate of electrical work that is done by a device or a circuit, and it is calculated by multiplying voltage and current, and it is expressed in the unit of watts, which is the SI unit for power. On the other hand, energy is the total amount of electrical work done by a device over a period of time, and energy is calculated by multiplying power with time, and it is expressed in the unit of joules, which is the SI unit for energy. For example, if we have a device that draws 1 volt for a 1 ampere current for 1 second, its power consumption will be 1 watt and its energy consumption will be 1 joule. So now that we have defined power and energy, how can we estimate the battery life of a device? Battery life is the measure of how long a battery can provide power to a device before it needs to be recharged or replaced. And battery life can be expressed in different units depending upon the type and the size of the device. And one common unit of battery life is watt hour. And 1 watt hour is equivalent to 1 watt of power that is used for 1 hour of time. And this unit is suitable for more power hungry and large devices such as laptop or tablets. For example, a typical laptop or a tablet may have a battery life of several tenths of watt hours. Another common unit of battery life is ampere hour, which is equivalent to 1 ampere of current flowing for 1 hour of time. This unit is suitable for less power hungry and small devices such as IoT devices. For example, a typical coin cell battery that we may have used in some of our devices that we use in day-to-day life have a battery capacity of about few hundred milliampere hours. As we have mentioned before, for small devices and IoT devices, we often use the unit of milliampere hour to estimate the battery capacity. For example, a coin cell battery like the one we show on the slide may have a capacity of 240 milliampere hour. And a flexible battery like the one from Molex, which is in a sticker form factor, may have a capacity of 10 milliampere hour. This capacity means that if you draw 1 milliampere of current from coin cell battery, it would last for 240 hours. Similarly, if you draw 40 milliamperes of current from the same battery, it would last only for 1 hour. Of course, we should be cautious that this is a very simplistic way of determining our battery life and lifespan. And there are often other factors that actually impact the actual performance on the battery. So for now in the slide, in the table, we show some of the current draw, typical current draw for various components that are typically used in IoT devices. We recall things like microcontroller, accelerometer, Wi-Fi, and Bluetooth radio. And as you can see, a microcontroller consumes only few hundred milliamperes of a few hundred microamperes of current, while an accelerometer consumes few to tens of microamperes. However, a Wi-Fi or a Bluetooth radio transmitters consume several orders of magnitude more power. They are typically few to tens of milliamperes of current. So let's go back and look at the battery capacity and look at how long would a battery last if we only power these components through these batteries. If we don't have any other component except that these components listed in the table individually are being powered by the battery. what we find is that typically a microcontroller can last for tens of hours on a flexible battery and thousands of hours on a coin cell battery. On the other hand, if you look at, for example, a Wi-Fi or a Bluetooth radio, it only lasts few hours or even only tens of minutes in the case of a Wi-Fi radio operating on flexible battery. And this is because of the larger power consumed by wireless communication module when compared to the other components of an IoT device. So next, let's examine the energy consumption for wireless communication in more detail. As we have seen that this is the most power intensive operation on a typical wireless or an IoT device. So let's look at a mobile device with battery capacity of about 9.62 watt hour. So first we look into a Wi-Fi radio. It has a transmit current of about 219 milliampere, a receive current of about 215 milliampere, and a voltage of 3.3 volts. Now, if we assume that only the wireless radio is in operation and we consider it for the calculating the energy consumption for the networking, we can estimate that the transmit power would be 722.7 milliwatts. And this gives roughly a lifespan, if the device is constantly transmitting, to be about 13.3 hours. Similarly, if we calculate lifespan for continuously transmitting using Bluetooth radio, it comes out to be 93.76 hours. So of course, this difference in the lifespan is primarily because of the difference in the power consumption between a Bluetooth and a Wi-Fi radio. And typically a Bluetooth radio consumes much lower power than Wi-Fi, but of course it transmits at a lower data rate as well as the lower transmit power. And so in the previous example, we assume that the wireless radio was constantly transmitting. However, this is usually not the case in reality. A wireless radio can have different states depending upon its activity and power consumption. In the ideal state, the radio is ready to transmit or receive a packet but does not do so. In the sleep state, the radio is inactive and consumes very little power. And the radio can switch between these states to save energy. And in the slide, I demonstrate this discrepancy in the power consumption between different states of a Wi-Fi and a Bluetooth radio. So let's examine the power consumption of a smartphone while it's transmitting information through a Wi-Fi radio. So on the graph presented in the slide, on the y-axis, we have the power consumption in milliwatts, and on the x-axis, we have the time in milliseconds. And what we find is that when the phone is sending small bits of information like beacons, it generates a very narrow spike. But when it is transmitting data, like for example, you are streaming movies, it generates much wider transmissions that occupy a large chunk of the spectrum. And the important point is that, for example, switching between these different states might not be straightforward because there is typically an overhead involved in terms of software and device drivers. So your phone may not find it easy to switch between different beaconing, data reception or transmission or ideal state in a short period of time. So let's look at another commonly used protocol for IoT device, and this is Bluetooth Low Energy. So this is the modern standard for Bluetooth that is designed for operating in the low power consumption and making it useful for devices such as IoT devices. And the Bluetooth device comes in 3 different classes depending upon the radiated power. For example, class 1 radiates power between 10 to 100 milliwatts, class 2 about 2.5 milliwatts, and class 3 about 1 milliwatt. It operates in the ISM band of 2.4 gigahertz, and it can allow you to generate mesh of point-to-point networks, mesh, or have support broadcast communication. So here, for example, we look at a typical power consumption for different modes for one of the particular radio chipset. So this is one of the earlier version of the radio chipset that you're using in sensor tag. It has a transmit current of about 6.1 milliampere when it is transmitting at 0 dBm. Of course, if your radio is transmitting at high transmit power, which is configurable, you might consume more current, as is the case for the next bullet point. it has about sleep current of 1 microampere. That means that it is in low power mode, and it's conserving energy. And your goal in some respect would be to keep your radio as much as possible in this sleep state, so that you can conserve energy of the battery. So typically what you find is that the radios on IoT devices go through a series of different states. So here we have a graph that demonstrates on the y-axis is the current consumption, and on the x-axis the time for one of the sensor platform called Mika 2. And typically you start that the CPU is in a low power idle state, and then it turns on, and then the radio is in the listen state. That means it can either transmit and receive at the very short notice. And then the radio starts to transmit, and the current consumption increases quite significantly, and the power and the current consumption for the sensor node is the highest when the radio is wirelessly transmitting. And as soon as the radio is transmitted, it goes back into the low power state, where both the radio and the CPU are in the deep sleep state, and the current consumption is very little. And on this graph, it looks like it is about 0. So as we have seen, a radio transceiver can operate in one of the 4 states: sleep, receive, idle, or transmit. And the power consumption of these states is not the same, and neither is the time it takes to switch between them. For example, it might take more time for your radio to switch from a sleep to an idle state than from idle to transmit or receive state. And of course, the power consumption is very different as well between the state. Sleep is much lower in power consumption than the idle state. And to maximize the battery life, we would want to keep the radio in low power state as much as possible, and only switch to a high power state when it is absolutely required. So here, for example, we look at the different low power modes that are available on the CC2650 device, which is the sensor tag. It has an ARM Cortex M3 microcontroller that can operate at a maximum frequency of about 48 megahertz. And its current in the active state can vary between 1.45 milliamperes to about 3 milliamperes. And just for comparison, if you look at, for example, typical laptop and desktop, we are talking about many orders of magnitude lower in power consumption. So here on this table, you can find the power consumption for different states. For example, things like when it is in active state, it's about 1.45 milliampere to 3 milliamperes. But when it is in idle state, it's about in hundreds of microamperes. And when it is in a very deep sleep state, either standby or shutdown, it's at the order of microamperes. So let's look at another example to look at how the different states actually allow you to increase the lifespan when operating on batteries. So let's look at 2 wireless radio interfaces. So Wi-Fi, it has 3 different states: transmit, receive, and idle, which has a current of 280 milliamperes, 180 milliamperes, and 10 milliamperes. And 15.4, which is Zigbee radio, which is commonly used on IoT devices, and it has a transmit current of about 30 milliampere, receive of about 18 milliampere, and idle of 0.426 milliamperes. So let's look at how duty cycling can help us extend the lifespan of the IoT device. So if we have 100% utilization, that means that half of the time you're transmitting and half of the time receiving without your network interface or radio being put into the low power state. What we find is that the average current consumption would be about 230 milliamperes, and for the Zigbee radio, it will be 24.4 milliamperes. And for let's say if you are utilizing 10%, the average current consumption would be about 32 milliamperes, and for Zigbee, it will be 2.823 milliamperes. And for 1% utilization, of course, proportionally, the average current would actually go down. So based on this, if let's say we wake up the radio every 10 seconds and send 10,000 bytes of data, how long would the typical battery last? So we will find basically that the average current draw for this case would be about 10.0216 milliamperes. And the average current draw for Zigbee would be about 1.372 milliamperes. And this can be calculated based on estimating the transmit time and then multiplying it with the appropriate factors that we have discussed in the previous slide. And by using this current and then using the lifespan of a battery, you can estimate what would be the lifespan for the battery when communicating wirelessly at these different duty cycles. So thank you very much.